Okay, hello everyone. Welcome to this tutorial session about the aerosol size distribution measurements, which is a part of the aerosol instrumentation session. Okay, so my name is Wang. I'm an assistant professor in the Chemical, Environmental, and Materials Engineering at the University of Miami. So nice to see you all. So before I start the tutorial, I would first like to list the references. So there are two textbooks that I want to raise or bring to your attention. The first one is the aerosol measurement, principle, techniques, and applications. And the second one is the atmospheric chemistry and physics from air pollution to climate change. I guess if you're working in the aerosol field, these two books are I would say, a very important tool for you to know more about aerosols. And I also want to thank the help from Dr. Chang-Yu and Dr. Jian Wang, one from Dr. Wu from University of Miami, Dr. Jian Wang from Washington University to provide their slides that I'll introduce in this session. So first, about the size distributions. So if you have gone through Dr. Pratim Biswa's tutorial session, you will know that the size distribution is one of the most important parameter if we want to understand the aerosol processes or understand the role of aerosols play in our Earth's climate or health systems, right? So if you just directly measure the aerosol size distributions, obtain a size distribution for the ambient aerosols, you will see that these aerosols actually exist in different size modes. For example, there's nucleation mode, which typically mean the particles below 10 nanometers. So these particles are formed from the gas to solid conversion, right? So there are chemical reactions, and new particle formation is getting more and more attention in the recent decade because people find out that this process can actually contribute more than half of the cloud condensation nuclei on our Earth, which can play a huge important role in our climate. As these nucleation mode aerosols further grow to like tens of nanometers, they are in the Aitken mode. And then there are a series of processes involved regarding the Aitken mode aerosols. And further, there are particles in the hundreds of nanometers, which are called the accumulation mode aerosols. And these aerosols can directly contribute to CCN upon the activation under the condensation environments. And then finally, there are coarse mode aerosols, which are normally generated from the wind blowing dust or let's say sea sprays, volcanoes, and so on. So to understand the atmospheric processes involved with the aerosols, we have to be able to measure the size distribution before we can guess any information related to these mechanisms. So then we have the question of how to measure them. There are actually a series of methods, like a wide range of methods to obtain the aerosol size distribution. And due to the time limit, we can only introduce a few of them, right? So we could collect these particles offline, right? And then further observe under microscope using these offline methods. So unfortunately, I'm not going to cover that. And then there can also be optical methods using the scattering or absorption signal of the particles to obtain the size distribution. That is also not introduced in this tutorial. So in this tutorial, I will split the aerosol size distribution measurement into particle sizing and particle counting. On the sizing part, I'll focus on two methods. One is the aerodynamic method, and the other one is the electrical method. And then regarding the electrical method, I will further talk about the electrical mobility classification, transfer function, data inversion, measurement with, let's say, with other needs, for example, with higher time resolution or with smaller sizes. And on the particle counting side, there can be methods associated with electrical methods, for example, using electrometers. I'm not going to cover that due to the time limit either. So I will just focus on a widely used method called the condensation method. There are condensation particle counters, or the CPCs, to obtain the concentration of the aerosols. And we could also use the condensation method to invent or to create some newer instruments that are bio-inspired under or using these condensation methods. And some of these instruments were actually invented by Dr. Wu in CAST. So first, we'll talk about the aerodynamic method. So if you have gone through Dr. Biswa's tutorial, he have introduced the aerosol inertia, right? So we could actually use the inertia of the aerosols to measure their sizes. For example, one of the most important parameter in the particle inertia is the stopping distance, which describes how far a particle can travel once they are stopped, or basically once the flow becomes stagnant, right? So one example can be shown is the case of an impactor, where the particles will first go with the flow, and then you put a stagnant wall, right, facing the flow. And then the flow can get diverted itself because the flow is just the fluid, right? So the air is made of like tiny molecules. They can flow anywhere they want. But the particles, due to their heavier mass, they have to um, make a longer bend, right? And if the particle size is too big, then their stopping distance is too long. They cannot get over this obstacle, and then they will get collected. So you can see that impactor actually can act as a size cutter to cut off the particles with larger aerodynamic sizes. And further, you can see the stopping distance is the multiplication of the relaxation time multiplied by the velocity of the initial fluid, right, or initial particle velocity. And further, the relaxation time is a function of the particle size and density, which is basically similar to the particle mass, right, or is related to particle mass. So because of that, the heavier particles, or the larger particles, will have a longer stopping distance and they will get captured by the impactor. And by using this idea, we could build an array of impactors, right? So by using the first one that cut off larger particles and the second one that cut off uh, like particles with medium sizes, right? Because they can penetrate through the first impactor here, and then so on and so forth, and until the last stage, which collects the smallest particles. And we call this combination of impactors as the cascade impactor. And right now, I would say the widely used cascade impactor is the TSI Moody impactor. So I'm showing a picture of the Moody impactor here. So you can see that normally these impactors contain 10 to 13 stages, and each stage will correspond to a different cutoff sizes. The first stage will cut off the largest particles, and then the bottom or the last stage will cut off the smallest sizes, right? And you can see that the last stage or the 13th stage can cut off particles with aerodynamic sizes down to 10 nanometers, which is already very small. But it's very challenging to further collect smaller particles. This is mainly because smaller particles have smaller inertia. And to collect these particles, we have to drive or to move them with a very high speed. But there is a limit on the speed of the particles. That is the speed of sound, because the flow rate here, or the flow velocity here, is actually limited by the choked flow through the final nozzle, right? So that's why we cannot go further lower, although 10 nanometers is already a very small size, right? So, and then you can see that here is a more detailed list of how each stage of the Moody impactor corresponds to different cutoff sizes and their associated Reynolds number, right? So we want to make sure that we do not develop turbulent flow, otherwise they will mess up with the particle trajectory. And because of the extreme condition in the last stage, since the velocity is getting close to the speed of sound, so now we're in the compressible air, or we have to consider the air compressibility, right? So the calculation regarding the particle deposition or the inertial impaction here is going to be different compared to the first stage. You have to consider the temperature change due to the compression and expansion, right, through this, I would say, near sonic nozzle here, right? So on that topic, I would have to say that Dr. Biswas built his PhD thesis on the cascading impactor design. So feel free to go over his PhD dissertation. And then I also want to mention that these will involve the design of the low pressure impactor or the micro orifice impactors. So another way to characterize the aerosol size distribution with impactor is instead of using the impactors and then measure their mass of the particles, so cascade impactor, to get the concentration, you can monitor the mass increase of particles, so you can get the mass concentration of particles. But at the same time, if you charge these particles, then they can carry certain number of electrical charges. And then if you can guide these charges out, then they will form a current, right? So the current will be related to the number concentration of particles. So this is a design of the electrical low pressure impactors, or the ELPI. I'm showing a picture of the ELPI that's manufactured by Ducati, right? So you can see basically the ELPI will charge the particles with a corner charger. So particles will carry certain number of charges. They'll go through different stages of the impactors. And then we can use electrometers to count the current, or to measure the current through each stage and further get the size distributions, right? I would say a relatively newer instrument to monitor the aerosol or aerodynamic size distributions is called the aerodynamic aerosol classifier, which is commercialized by combustion. So in this system, it's actually using the spinning movement of two cylinders to separate the particles. So the method, or the process that's happening in this system, is that we'll first introduce the aerosols into the gaps between these two cylinders. At the same time, the cylinder will have this rotational movement or spinning movement. As you can imagine, or similar to a washing machine, right? So the larger particles, heavier components, will get spin to the outside, while the lighter particles, smaller particles, will follow the streamline here, right? And they will not get collected or impact onto any wall. So under certain velocity of the spinning movement, only particles with certain aerodynamic sizes can get classified or enter or exit through this outlet here. And further, you could collect these aerosols, right? And then further measure their number concentration. So in this way, you can monitor, or you could classify the particles based on their aerodynamic size and then monitor their concentration. So one advantage for this aerodynamic aerosol classifier is that it does not rely on the charging of the particles, right? So particles can be neutral, and they can get classified just based on their inertia. So in this way, you can enhance the counting statistics of the particles, especially if they have a smaller size, because smaller particles are difficult to charge. But still, since this is using the aerodynamic size, using the inertia of the particles, as we know, smaller particles have smaller inertia. So it's becoming more challenging to classify particles with smaller aerodynamic sizes. For example, the AAC here can classify particles or monitor the aerosol size distributions down to 20 nanometers, right? Because below 20 nanometer, or let's say below 10 nanometer, particles are too light. They will just behave like the air molecules, oxygen or nitrogen, so they cannot get easily spin outside. I would say the most widely used instrument to nowadays, right, or to if people want to monitor the real-time aerodynamic size distribution, people will rely on this aerodynamic particle size, or the APS. So the APS uses two laser beams to monitor the aerodynamic size distribution of the particles. Although it's using laser, it's not necessarily monitoring the optical size of the particles. It's actually monitoring the time of flight of the particles between these two laser beams. So if we write out the equation that's explaining the movement of the particle through these two lasers, you'll find out that the acceleration is dependent on the drag force on the particles. And at the same time, for this nozzle here, it's actually using a very large flow speed, close to 150 meter per second, right? Because of this large flow speed, you can generate a relatively large velocity difference between particles and the flow. So in this way, you can create a relatively different a range of drag force where you can separate the particles. So on the right-hand side, this describes the drag force, and you can see that the movement of particles is just dominated by the aerodynamic size of particles. It's if you assume all of them have the same density, right? Or this is getting the, I would say, when we describe the aerodynamic size, we assume that the density of the particle to be water. So you can actually use the time of flight to accurately derive the aerodynamic size of the particle. And further, depending on how many particles are being detected by the laser here, you can get the size distribution or the concentration of the particles. So this method can apply really well for the solid particles. So you can see if you have solid particles, they can get very high counting efficiency, close to 100%. But if you're dealing with liquid droplets, then you may have an issue. That's mainly because if you're introducing droplets into the system under this high flow speed, then these droplets can change their shape, right? Instead of having a spherical shape, they will change into a flat, like circular shape. And then the drag force will be very different compared to the spherical particle. And at the same time, because of this high flow speed, then these droplets can get fragmented, right? So you lose the particles fragmented into smaller or tiny droplets. So you cannot detect them very easily. So this is about the APS. So that's it about the aerodynamic method for monitoring the size distribution. So now I'll spend quite a bit of time talking about the electrical method and how we can use that to classify particles. I would say the most important or the most widely used instrument to monitor let's say the submicro particle size distribution is called the scanning mobility particle sizer. So TSI is a major supplier of the scanning mobility particle sizer, the SMPS. As you can see in our lab, later on we have several of these instruments. But at the same time, there are other models of SMPS. So you can see this is the older model of the SMPS. This is newer model. And then there are some companies in the United States or in Europe that are manufacturing their own SMPS, right? But you can see one thing in common. That is, they all have a single column, have a control box, and then they have a separate device, right? So if you summarize their commonality, actually, you can divide the SMPS system into three components. That is the electrostatic classifier, which contains the flow or high voltage, and then the control module of the SMPS, the differential mobility analyzer, the DMA, that classify particles based on their electrical mobility, and then the condensation particle counter, or the CPC, right? So the DMA will classify particles of specific sizes, and then CPC will count the number of the particles with that specific size. So because of that, in terms of sizing, the DMA will be very important. So here it shows the schematic diagram of the DMA system. So you can treat DMA as two concentric cylinders again, although right now this time it's not spinning, right? It's just fixed onto this whole SMPS system here. So these two cylinders are conductive, made of metal. So then the inner cylinder is connected to certain high voltage and the outer cylinder is grounded. So you can introduce the aerosols from the side of the outer cylinder. So they will get introduced into the gap between these two cylinders. And at the same time, there's a clean particle-free sheath flow that are being introduced into the gap between these two cylinders. So the sheath flow will also normally have a much larger flow rate compared to the aerosol flow. People normally use a 10-to-1 ratio, right? So now you can imagine if there's no electrical charge or no voltage, then the particles will just move downwards because of the sheath flow, right? And then they can never get any motion in terms of the horizontal movement, in terms of the horizontal direction. And now, if we charge the inner electrode, give it certain high voltage, and at the same time, if we charge the particles with certain sources, right, and then we can achieve a separation of the particles. Because, for example, if you give it a 1,000 positive voltage, right, positive volt, or plus 1,000 volt, and then it can classify actually to attract negatively charged particles, and then particles with specific sizes can get classified and then further get counted by the CPC, right? So when certain voltage is being applied onto the center electrode, only particles with certain sizes can get classified. And now, if you change the voltage or scan the voltage that's being applied onto the center electrode, then what you see from the CPC is going to be particles of different sizes, right? And in this way, you can get the size distribution of the particles. And that's why it's called a scanning mobility particle sizer. So here is a diagram of the system again, right? So this represents the, let's say the inner electrode, right? Where you have the exit or aerosol exit here. This is the outer electrode, right? And then where we have the aerosol inlet. So the aerosols will be, let's say ambient sources or any sources can first get charged by a bipolar charger. So here we use a bipolar charger mainly because the bipolar charger is well characterized in terms of charge distribution. So we can confidently say which portion of particles carries +1 charge, +2 charge, -1 charge, or -2 charge. And then these particles can get classified. So here it shows the trajectory of particles of different sizes. So you can see smaller particles will move faster towards the center electrode. Our larger particles will move slower towards the center electrode. And only particles with the medium size or specific size can get classified. So we'll talk about why smaller particles move faster later on, right? So then after the particles are classified, they have a relatively narrow size distribution, and then you can measure their concentration with the condensation particle counter or the CPC. So now let's talk about the electrical mobility because it's using, or the SMPS is using electrical mobility to classify the particles. So the electrical mobility is defined as the velocity or the migration velocity of particle normalized by the field strings, right? And further, at the steady state, the drag force is balanced with the electrostatic force because the particles, there are only two forces of the particles that are being applied onto the particle. The gravity, although there's gravity, but the gravity is too minimal or negligible compared to the other forces. So then you can build up this equation due to the force balance, right? So you have QE, which is the electrostatic force, equals the drag force, which is 3 pi mu dp multiplied by velocity divided by the Cunningham slip correction factor. This is a drag force. So now you can consider smaller particles and larger particles. So here in the SMPS system, most of the particles will only have one charge, right? And then if we just consider small particles or large particles with +1 charge, right? And then they will have the same electrostatic force being applied onto them. And because of that, the smaller particles will have a larger velocity, right? So that's why they will move faster towards the center electrode. And then the larger particles will have smaller velocity or the migration velocity. So because of this reason, we can separate the particles based on their sizes. That's why when certain voltage is being applied or certain electrostatic force is being generated between these two cylinders, only particles with certain sizes can get classified. Right. Further, the C here is a Cunningham slip correction factor. Although it's a function of particle size, it doesn't necessarily change this trend here, where the smaller particles will move faster, larger particles move slower under the same electrostatic force. And further, the particles the movement of particles, or especially the Cunningham slip correction factor, is dependent on the size of the particle, right? So we can divide the motion of the particle into different regimes, like the free molecular regime, transition regime, or the continuum regime. The continuum regime means that when the particle size is much larger than the mean free path, then the Cunningham slip correction factor can be treated as 1. And in the free molecular regime, the Cunningham slip correction factor is actually proportional to 1 over dp, right? And then the transition regime is has the particle size in this range here. But overall, there is a 1-to-1 correspondence between the electrical mobility and the particle size, which means that if you know the electrical mobility, you know what the particle size is, right? So because of this reason, we can separate the particles. Again, smaller particles will move faster towards the center electrode, larger particles move slower towards the center electrode. Now here I'm showing you two pictures of the DMA system that are commercialized by the TSI. So you can see there is a TSI long DMA, which is targeted for particles with sizes between 10 to 600 or 700 nanometers. And the nano DMA is targeted for particles, let's say above 2 nanometer to around 200 nanometers. But the main reason for in terms of their size or the size range is because of the length for the DMAs. As you can imagine, if you have longer DMA, then you can classify larger particles, right? Because they move slower towards the center electrode, right? But there are advantages for the nano DMA, which is if you have a shorter separation region, then you can reduce the time for the particles to be classified. And then you can reduce uncertainties associated with the Brownian diffusion of the particles. We'll talk about Brownian diffusion later. There are other geometries of the DMAs. So the cylindrical DMA are not the only one. There are parallel plate DMAs, and there are also these radial DMAs. So in the radial DMAs, the aerosols are being introduced from here, right, from the bottom of these two plates here. And then the clean sheath flow are being introduced from the outer ring. So they still go through the gap between these two plates, right? And then you have the voltage being applied between these two plates. And then the particles will get attracted, or basically particles carrying charges that are opposite to the voltage are getting attracted and get classified. And then the remaining particles will exit from here, right? In this way, you avoid the longer dimension of the DMA, so we can make it more portable or miniaturized. And based on this radial DMA, there's spider DMA that are designed, which is mainly to distribute the aerosols more evenly through this ring here, because you cannot just introduce aerosols at one single point, right? And to evenly distribute these aerosols, you need tubes of similar lengths. So that's why they have these tubes or aerosol distribution tubes that looks like spider legs. And then this is how the spider DMA looks like. So now we'll talk about the transfer function and the data inversion. Okay, so the transfer function of the DMA, or any instrument will have a transfer function, right? So the transfer function of the DMA is mainly defined as the probability that a particle of mobility Z will be transmitted from the aerosol flow to the monodispersed sample flow. So it may sound a little bit complicated, but if you imagine, for example, if we give certain voltage, let's say 1000 volt onto the center electrode, and we're trying to classify particles of different sizes or different mobilities, you can think that most of the particles will not get classified, right? Because their size just won't match with this specific size. But around that specific size that correspond to 1000 volt, then the particles will get classified. And there will be a specific size of the particle that can have a highest, let's say, retrieval efficiency that will get introduced from the inlet and then exit through the outlet. Excuse me, right? So this is the definition of the transfer function. So we would like to see what is the probability of particles with different sizes when a specific voltage is being applied onto the center electrode. And on this topic, I would have to say there's a, let's say, a very classical paper that is published by Newson Whitby, right? I would treat that as a Bible for the DMA system. So it has a very elegant derivation of the transfer function for cylindrical DMAs. You can feel free to go through those equations, and probably it will just take 1 hour for you to both or derive all of these transfer function equations. But overall, if you consider the trajectory of the particles that are going through the DMA in the system, then, for example, if the DMA voltage is being set up to classify 100 nanometer particles, then if you have 100 nanometer particles being introduced into the system, then no problem. All of them will get classified. But what about particles of smaller sizes? For example, 99 nanometer or 101 nanometer. Are they going to get classified? The answer is yes, right? If you consider 99 nanometer particles, as we mentioned, smaller particles move faster towards the center electrode, right? So because of that, they will their trajectory will go upward. But at the same time, some portion of the aerosols may still go through this outlet here and get classified and get counted. The same thing for 101 nanometer particles, right? These larger particles don't go downstream, but some of them can exit through this outlet here and then further get counted. So from this derivation here, you'll find out that actually the transfer function of the DMA has a triangular shape where the voltage or the particle size or the mobility corresponding to this specific voltage will have the highest probability of getting classified. And nearby this mobility here, or this centroid mobility here to the left or to the right, particles can also get classified. And there is a resolution for this classification, which is defined by the centroid mobility divided by the full width at half maximum, right? And people find out that this resolution is directly equal to the ratio between the sheath flow and the aerosol flow. Okay, so this is how the transfer function looks like. Then you may wonder, well, why is it important? So if you use the SMPS system and then you set the DMA voltage to 100 nanometer to classify 100 nanometer particles, and the CPC is giving you 100 particles per cc, isn't that enough? Doesn't that tell you particles 100 nanometer is exactly 100 particles per cc? No, it doesn't. It's mainly because we have this transfer function mechanism here that particles of 99 nanometer or 101 nanometer are also getting classified. And to make things more complicated or sophisticated is that we also need to consider the charging efficiency of particles, because not all of these 100 nanometer particles are charged. Some of these particles might get lost in the system. So you need to consider the penetration efficiency. The transfer function we already introduced. And then there's also CPC counting efficiency, especially when you're counting smaller particles, let's say below 10 nanometer or below 3 nanometers. So because of that, you have to consider or derive the size distribution using a data inversion. So here, in addition to the transfer function or this triangular shaped transfer function, people also consider how diffusion of the tiny particles might affect the shape of the transfer function, mainly because if you're classifying smaller particles, let's say below 10 nanometers, then the Brownian motion of these particles will become more significant, right? So they will deviate from their original trajectory. So their concentration will get smaller, right? Corresponding to the centroid mobility. And at the same time, particles with different sizes, smaller sizes or larger sizes, will also get classified. And this image here shows you how the transfer function shape is dependent on the Brownian diffusion of the particles. So here, different lines represents the different voltages corresponding to that are being applied onto the DMA. The lower the voltage, the smaller the size that corresponds to this voltage. So you can see when the DMA voltage is corresponding to 1 volt, which is probably close to 1 nanometer of the particles, then the transfer function looks really flat. This is because 1 nanometer particles diffuse much faster compared to when you're classifying particles with 10,000 volts. They're very large, right? And then in terms of the charging efficiency, not all of the particles are getting charged, right? When you're trying to charge very small particles, their charging efficiency is very low. For example, if you want to consider particles carrying +1 or -1 charges, right? So at, let's say, 10 nanometer, only 3% of them or 4% of them are getting charged, right? So we have to multiply this 25, this ratio here, back to the measured CPC concentration to get the actual size distribution of the particles. So to consider this entire process here, now we can understand that the response of the CPC basically just give you the concentration of particles that are at the exit of the DMA. But this concentration is really dependent on the actual size distribution, which we don't know, and then the penetration efficiency of the particle, the counting efficiency of the DMA, the charging efficiency of the particle, and then the transfer function, right? This is a convoluted integral of all the different terms. And here there's another summation sign here, mainly to show that not all of the particles are singly charged. So multiply charged particles may also get classified from the DMA, right? So for example, you have 10 nanometer particles singly charged. You may have, let's say, 15 or 20 nanometer particle, or between 15 and 20 nanometer particles carrying doubly charged, and then they can also get classified, right? As long as they have the same mobility. So that's why you have to consider different charging scenarios. So this involved the process of how to invert this unknown size distribution based on all of these known parameters, although it's in the integral sign. So people have developed this data inversion algorithm, which is first to break down this integral into different size bins. So you break that into a summation, and then further, you can bring the concentration out of the summation, assuming that concentration doesn't change much in the transfer function region or in this integral here, or in this particle size range here, right? And this is most of the time the actual case, mainly because, let's say, for ambient aerosols, you have a very wide size distribution, right? So because of that, since the terms inside this integral sign here is already known, right? So then it comes to the question of, based on the CPC concentration at different voltages, how do you get the size distribution at different size bins? So you can convert this further into a matrix calculation, right? You can measure the concentration at different voltages, and then this is unknown size distribution. You have the inversion matrix here, and then this problem gets converted into a matrix calculation. So currently in the aerosol field, there are two major methods for deriving the size distribution using data inversion. So one is the Toomey inversion method. There are two methods, papers listed here. There's also a non-negative least squares matrix inversion. It's called the L curve method, right? So reduce the uncertainty with the size distributions. So this is it about the data inversion. So basically you can see the size distribution that you see from the, let's say, the TSI software is not as simple as you thought, right? So you have different mechanisms to consider when you're trying to get the accurate size distributions. So now I'll briefly talk about the different needs for the aerosol size distribution measurement. So first is the measurement with a high time resolution. So again, if we go back to the SMPS operation, you can see that you have to scan the size distribution. If you have operated the SMPS system, you know that this normally takes 1 minute for the entire scan, right? The newer model can give you 30-second scan, but it's still relatively long time if you're considering very transient processes. For example, if you're interested in aerosols with intense formation growth, for example, combustion, because the aerosols are being formed at the ignition or extinguish process may be very different compared to the steady state burning condition. And also, many studies actually use these research aircrafts to monitor the aerosol size distribution. And these aircrafts moves with a large speed, right? Close to 100 meters per second. And then if you have a scanning time of 30 seconds, then that means the aircraft is already 3 kilometers away from the original location. So you lose the spatial distribution or spatial resolution in terms of the aerosol size distribution, right? So because of that, there are needs for newer instruments, other instruments that has high time resolution and also have high accuracy in the submicron range, especially below 100 nanometers. So because of that, there are these electrical aerosol spectrometers, for example, the TSI EAPS, FMPS, or the combustion differential mobility spectrometer, DMS, right? So they're still using the mechanism of the DMA and then classify particles based on their different sizes. Like smaller particles will get classified here, larger particles get classified at the end. But electrometers are normally limited by the counting statistics because the most accurate or the most precise electrometer can achieve the resolution or accuracy of 0.1 femtoamp, right? That still corresponds to like hundreds of particles per centimeter cubed. So you still have to accumulate enough signal to get the accurate size distribution. So they're limited, mostly limited by application with high concentrations. So we need to design instruments that are sensitive to low concentration aerosols. And during my postdoc research at Brookhaven National Lab, I worked on an instrument called the Fast Integrated Mobility Spectrometer that is using these CPC mechanisms to count the particles. So it's similar to the DMA, except that now you have 2 parallel plates. and then one plate is connected to the ground, the other plate is connected to the high voltage. And then the particles are getting introduced into the gap between these two cylinders. Smaller particles move faster towards the charged electrode. Larger particles move closer to the, or move slower to along the grounded electrode. And after that, they'll enter this grounded low temperature region. We call this condenser. At the same time, we should notice that there's again clean sheath flow, but we saturate the sheath flow with heptanol vapor, alcohol vapor. So because of that, in this condenser, which is operated under lower temperature, then these vapor are going to grow onto these tiny particles until they are supermicro droplets. And at the end of the fins, or these two parallel plates, we have a horizontal laser sheet that shines across or shines through this gap here. So then any particles that's going through this laser sheet will get illuminated and further get recorded, right? So this is how the instrument is designed. So if you want to look at an animation, right? So if we go look from this angle here, and then the here's a short animation showing you how the particles are getting through this system and get recorded. So first they go through a bipolar charger, right, to pick up the charges, and then they'll get separated in the mobility separator, and then in the condenser they grow into supermicro droplets, and then the laser will shine upon these particles, and then you get the location or get the illuminated particles. And further on this image here, the location of the particle is actually related to the mobility of the particle, because smaller particles get separated faster, larger particles get separated slower, right? So the location is related to the size of the particle, and then the number of particles at each location is actually going to correspond to the concentration of the particles. So here we're introducing particles of specific sizes, 100 nanometer. And then you can see that they can actually align in a straight line here, right? This is how the camera or the picture looks like. And then this is an animation of the picture we collected, or a movie of picture we collected. So you may think that the particles are flowing up or down, but actually the particles are just going through this, through the screen, right? So it's just going through this channel and then get recorded. But you can see that even though we're introducing particles of specific sizes, they still have a distribution. And this is mainly because the inlet cannot be infinitely small. But more importantly, the aerosol flow will create a spread of the aerosols. So because of that, you cannot get a very thin distribution of particles. The Brownian motion will also play a role in distribution. So because of that, we further designed or updated the FIMS system so that it can accommodate a wider size range. I'll skip the discussion on that. Feel free to let me know if you're interested. But we tested the FIMS system and compared it against the SMPS system. So you can see the two instruments agree really well, right? But more importantly, the FIMS can provide these concentrations at a much higher speed. So you can achieve a resolution of 1 Hertz. So we have used this system in several research campaigns operated by DOE or NASA. And then you can see from the size distributions, we can integrate them to get the total concentration, number concentration, right? And then they compare really well against the CPC in terms of total concentration. But more importantly, you can see that from these short-timed spikes, we can analyze what is the size distribution of the particles during these short events, right? And then we can trace them, since they're observed onto the aircraft, we can trace them to a specific location, and then to understand the process that's going. So this is about the time resolution. There are also needs for monitoring particles with smaller sizes. As I mentioned, particles of smaller sizes tend to diffuse more, right? So for example, when we're classifying 3 nanometer particles with the long DMA, then you can see particles of small as 3.88 and or as large as 3.88 and as small as 2.54 nanometer are all getting classified. And one way to reduce the Brownian motion is to just shorten the particle residence time. So if you consider the non-dimensional number that are involved in this process, that's going to be the Peclet number. where you need to increase the velocity of the particles, right? So in this way, you can suppress the diffusion of the particles. So this is where the design of the high resolution or high sheet flow DMAs are coming into the picture. So these high sheet flow DMA normally operate with a sheet flow of larger than 200 liter per minute, which is significantly higher compared to the conventional SMPS system. And because of that, you can see that they can achieve a very high resolution when we're trying to classify particles of smaller sizes, right? So you can generate these highly defined peaks when, especially for the sub-3 nanometer particles. So we use this system to look at particle formation in combustion, and then you can actually see how the particles are getting formed when they're having the gas to particle conversion, where they first form stable clusters and then they combine and further form larger particles through the coagulation, condensation, and these different mechanisms. We also collected these particles offline, and then you can see they actually agree pretty well with the AMF or atomic force microscopy in terms of their physical size distributions. So finally, I'll briefly talk about the particle counting. So as I mentioned, the particle counting, or the most widely used instrument for particle counting, is actually the condensation particle counters, right? So first we'll talk about the condensation mechanism. So condensation is basically a process of particle size growth due to vapor deposition in the presence of condensation nuclei or ions. So we see these condensation scenarios every day. For example, our window from the plume, right? Or let's say it's a smokestack where you have a highly concentrated water vapor, and then when it's being emitted into the cooler ambient environment, the water will condense onto the existing particles. And then same thing for the clouds, where you have the tiny aerosols rise up adiabatically, and then as temperature cool down, the water will condense onto the particles and form clouds, right? So if you want to theoretically or mathematically understand this process, there are equations describing the condensation mechanism. So here we'll just focus on the continuum regime because the derivation for the free molecular transition regime, there are also equations in there, but continuum regime equations are relatively more simple, right? So first, you can describe the distribution of particle or the vapor concentration at any location when you're considering a spherical particle in the system, right? We're using the spherical coordinates or polar coordinates to describe the equation. So by assuming that everything is under steady state, you can create this equation to 0, right? And then you can find out what's the distribution of the water vapor or any vapor in this system. And then you could calculate what's the flux or concentration difference and calculate the flux towards the center particle. And then this is going to be the rate of diffusion of condensation. You can see that it's dependent on the particle size. The larger the particle, the faster the condensation, and the diffusivity of the vapor, and then the pressure difference or the concentration difference between the concentration difference of the vapor between infinitely far away and at the surface of the particle or the droplet, right? And then you can build up this equation. Since you know the condensation rate, the condensation is getting added onto, or the volume of the vapor added onto the particle is going to cause a volume change, right? So you can directly equate this rate to the change of the volume. So you can see the change of the volume is proportional to the size of the droplet or size of the particle, right? So basically the larger the particle, the faster the volume change. But you could also derive or write out the expression for the volume, which is pi over 6 multiplied by dp to the third. And you can find out that the particle size, the change of the particle size is proportional to 1 over dp, which means that if you have a relatively large droplet, then their size growth is going to be slower, right? So the growth rate in terms of particle size is actually dependent on the particle size. The larger particles will grow slower in terms of size. So are there implications? right? So here is a simple example problem. And due to the time limit, we're not going to derive these equations. But if you have two particles of initial sizes of 0.1 and 1 micrometer and expose them under the same vapor concentration scenario, and then after 1 second of condensation or growth, you can find out that they actually grow to the same size, 57.7. This is mainly because the size grows, right? The rate change of the particle size is proportional to 1 over dp, which means that the larger the particle, the slower the size grows. So eventually they have the similar sizes. So the implication is that if you measure the droplet size distribution in the cloud, they're actually having the similar size, right? So in a condensation system, particles grow to the same size. They'll have the homogeneous size distribution regardless of their initial sizes, if there is sufficient vapor for particle size growth. So basically, if you grow these particles in a device, no matter what initial size distribution they have, they're going to have the final similar droplet size distribution. So using this mechanism, we can grow the particles in the condensation particle counter. And then basically, after they grow to similar sizes, you could just use a laser and then to count the particles, right? So when they pass by the laser, it scatters light, and then you can get the photo detector is going to get the signal. But at the same time, as we know, the light scattering efficiency for particles of different sizes are different. That's where the advantage of the CPC come into the picture, because after you grow them, they're having a similar size. If they have similar size, they have similar scattered light intensity. So in this way, you can achieve an accurate counting of the particles. So then, can we use the CPC to measure particle size? No, but you can combine the DMA with the CPC to get the size distribution. Using the condensation method, you could also generate particles, because after condensation, they're going to have a similar size, monodisperse size. So this is where people can generate particles of different sizes, right? You can see larger and smaller ones, but then you let it go through the evaporation and condensation, and then you can get particles of monodisperse size, or approximately monodisperse size, for calibration or for other purposes. So here we have mostly focused on the butanol system, but there are also CPCs that are built on water systems, right? So, but the conventional CPCs actually do not perform well with water, mainly because water actually diffuses faster than heat, right? So if you look at this scenario, if you have the butanol CPC, then when you introduce the particle into the system, right? So the butanol vapor are actually going to grow onto these particles, and then because the heat diffuses faster, right? You have a colder environment here, and then basically in the condenser, the heat diffuses faster towards the center, where you can achieve a higher supersaturation near the center. But when you have the water in the system, then water actually diffuses faster than heat. So because of that, you will not achieve a supersaturation. Here, you just get subsaturation. We can never grow the particles. But we could actually reverse this temperature setting. Instead of having a cooler region, we have a hotter region to grow the particles, right? Because water can diffuse faster than heat. So using this mechanism, we can build a water-based CPC to count the particles. And more importantly, this actually enabled a range of bio-inspired systems that are using water condensation. One example is the biovirus aerosol sampler. So this is developed by or invented by Dr. C.Y. Wu at the University of Miami. And then basically a lot of these aerosol or bioaerosol capture experiments, they do not consider the viability of the aerosols. So you either collect them into a filter where these aerosols virus got inactivated, or people just collect them into the liquid, where you lose the aerosol properties of these virus or bacteria, the pathogens, right? So we could use the water condensation method, where you can first cool the aerosols and then warm it up. So if you warm it up, then the water diffuses faster, they can grow onto these droplets. And then you may want to remove the excess moisture to basically to remove the extra water from the droplet growth, and then they can be further deposited onto the cells or onto petri dish where you can do further analysis of the pathogens. So you could also use that for the for simulating the or to understand the toxic effect of the aerosols, right? In our human lung, we're actually creating these highly saturated, highly moisture environments, right? So when we inhale the cooler air inside, the high concentration of water vapor are going to grow onto these particles and make them droplets. And once they're droplets, they will deposit onto the lung epithelial cells and create some toxic effects. So this is where the design of the dosimetric aerosol in vitro inhalation device, or the DAVID, come into the picture, right? So it's mimicking the human lung system, where you grow these particulates and then you can further deposit them onto the cell lines and then to understand the toxicology effects of the aerosols. So compared to the, so this is a well-controlled engineering deposition method, and compared to the currently used or widely accepted method, which is generating a cloud of aerosols and deposit onto the cells. So this method can achieve the DAVID can achieve a high deposition efficiency of the aerosols. While compared to the cloud aerosol deposition, they're just using the gravitational settling, and you cannot really control the dose very well. So that's the end of this tutorial. And as a summary, in this session, I talked about the particle sizing and counting methods. In sizing, I introduced the aerodynamic method and electrical method, especially regarding the proper usage of the SMPS system. And then on the particle counting, we talked about the CPC and then the condensational methods, and then an array of other instruments that are using the condensation mechanisms. So that's it for this tutorial session. Feel free to let me know if you have any questions. Thank you.